All right. So first thing is just to remind you again. Mentioned this yesterday. Our next test, third test, is coming up soon. Coming up Monday, and we'll go up through what we covered today. We're going to finish up everything that we're going to do in Chapter 7 today. We got one more topic to cover, and that'll be the last thing you're responsible for on your test on Monday. So 11 o'clock, same as before. I'll open it up a little before 11. So if you want to get started a little before then, that's fine. You'll have 60 minutes again from the time you actually open the test and start working on it. Same process, procedures as the first two tests. Should be familiar with that by now, but I will send out an email probably tomorrow in case you deleted or misplaced the last time I sent out the process and the procedure. I'll send that out again to you tomorrow just to remind you. But test coming up Monday. Tomorrow during class, the first half, we'll start talking about new topic. We're going to skip ahead and talk about designing beams. And the second half, we'll spend talking about the test that's coming up Monday. All right, so that's what's in the near future. Anybody got a general type question about what's coming up before we knock out this last topic? All right then. Move this out of the way. So, thing we're going to talk about today, you'll find in your textbook in section 7.3, and we're going to talk about shear stress, still continuing our study of shear stress. But we're going to look at kind of a special case, a special situation here. We're going to look at a particular kind of beam, and we refer to these, are called these built up beams. So a little bit about this terminology we're using here. It's a fairly common way to construct a beam is to take some longitudinal members and somehow or another fasten those together. Either if it's wood, by nails, or maybe if it's steel, you might bolt them together, or use rivets or spot welds, or somehow or another you take these members and you basically construct the beam by fastening two or more members together. And that's what we're going to talk about today. And we're going to focus on the fasteners, right? Because essentially what we did yesterday was analyzing the beam. And if the beam is constructed this way, you would also need to make sure the shear force or shear stress on the fasteners is not too large. Because if the fasteners fail, obviously the beam is going to fail, right? So, but first, what we're going to consider here is not a built-up beam, but a solid. Let's spell solid. A solid one piece. We're going to look at a T-beam, but it's solid one piece. Cross section looks like a T. So if we look longitudinally from the side, we've got this T-beam, and we're going to bend it. And we're going to apply this bending moment. Beam's got some length L. Now, if we look at the cross section, it's going to look like a T. All right, so that's what the cross section would look like, and we know our neutral axis. And so part of this is actually good review from previous discussions. We know our neutral axis goes through the centroid. So if we were actually going to calculate the bending stress or the shear stress in this beam, we would need to first locate where that centroid or that cross section is. And assume that this T-beam, the web here's got some thickness T. Now, if we wanted to find what the shear stress was right here on, we'll call this AA. So if we wanted to, looking at this is also a good review from yesterday, the maximum shear stress in the beam is going to be at the neutral axis. Because remember, the minimum thickness is at the neutral axis. So that's where tau max would be. But that's not what we're going to calculate here. We want to find the shear stress at this location. Right? So if we want to find the shear stress here, our formula VQ over IT, Q here would be for all the area above this plane AA, and T would be the thickness there at that section. Now, when we calculate this Q, remember, it would be all the area above that. So this area, just the cross-sectional area of that top flange, that's what we would use to calculate Q. And it would be that area A prime times this distance Y bar prime. That's what the notation uses. And that's the distance from the neutral axis to the centroid of that area A prime. So that's how we would calculate this Q. And this is how we would get the shear stress here at that location on our cross section. So that shear stress, if you look at, I can try to draw a three-dimensional picture here. Let me draw a straight line. Well, that didn't turn out too good. Pretend like that's not there. Again, I never professed to be a great artist. All right, so basically what I've done is I've sliced this beam longitudinally right at the top of this web. So this would be, what we're looking at, AA there, right? And this would have some width T, some length L. But there's a shear stress going to be acting on that longitudinal surface. That's what this formula actually calculates and gives you, is this shear stress on that surface. Right, so this would be the shear stress on that top surface of that web. All right, any questions at this point about what this formula and how we get Q and which shear stress we're talking about? Right, so again, this would be the shear stress on that surface if this was, again, solid all one piece. So now what we're going to do is consider the same beam, spell here, but instead of being one solid piece, let's say we have two pieces, and maybe we'll assume these are wood, and we're going to nail them together. All right, so we're going to construct the same beam, and again, I'll try to draw a 3D picture here. All right, so now we've got this top piece, this flat rectangular piece, and then we've got this other piece, the vertical member, and try to draw a straight line again. All right, but instead of, again, being one solid piece, we're going to take two pieces and we're going to attach them together like this by placing that one piece on top of the what would make the web, and coming in and driving this row of nails down the top of that thing to attach these two pieces together. And we're going to assume, or denote anyway, the spacing between the nails. We're going to denote with S. And for our purposes, we're going to assume all of these nails are spaced the same distance apart. And that'll be true for anything that we look at in this section. Okay, we're not going there where you have variable spacing. Right? We're going to assume uniform spacing. So we're assuming all of these are spaced the same distance apart. So between there and there would also be S, between here and here, same distance, S. All right, so those, in this case, nails, but it would be true any kind of whatever fastener that you're using, but those nails must take the same shear force as the solid surface above. So if I draw a 2D picture here, again, we're looking at this top surface of that vertical member. Again, what we had before, right? We had this shear stress. Right, that's our shear stress from up here above. Now up here, if it's one solid piece, we've got all of this surface area to take that shear stress. But basically what we're going to do is we're going to replace this big rectangular area with these finite, discrete, in this case, assuming we're going to be using circular nails with circular cross-section. Right, so instead of having all that area, all we've got here is just the cross-sectional area of the nail. But it's got to take the same force as that solid thing did. Now, keep in mind, remember these are spaced, some distance S apart. So basically, if you look at one of these nails, right, that one nail has now got to take the same shear force as this rectangular cross section did before. And don't forget, this is got some thickness T. So the shear force on that one nail remember how we get force is take stress times area. So we would take that stress, tau A, and multiply times the area it acts over. Now, this would be, that rectangular area there is the surface area that stress is acting over. Well, we know from up here that stress is BQ over IT. That area is a rectangle. It's going to be whatever the spacing S is times the thickness T. T times S. All right, well, this thickness is the same, right? This TA here is the thickness of the web. So those teeth cancel. And so what we wind up with is this formula. Shear force on each nail is equal to VQS over I. Now, make sure everybody is clear here with what everything represents and stands for. Again, FS, that is the shear force on each fastener. Again, for our example, we use nails, but it doesn't matter whether it's a nail, a rivet, or bolt, whatever the fastener is. That's what FS is. It's the shear force on each fastener. V is the same as it was in previous. That's the internal shear force. It's acting on that cross section. We just go in order Q here. Again, it's Y. Well, let's do A prime times Y bar prime. So in this case, in our example, this would be our A prime. Right? It's all the area above where that fastener attaches that, in this case, that top flange. So make sure you remember that A prime here is the area that's attached by the fastener. Right, so when you look at this cross section, whatever area is attached by that fastener, in this case a nail, that's where you're getting Q is for everything above that. So when you calculate Q in this formula, you're just going to use the area A prime that's attached by that fastener. Let's see. S, again, is the longitudinal spacing between fasteners. And I is the same as it's always been. It's the moment of inertia for the entire cross section about the neutral axis. Again, this would be moment of inertia for entire cross-sectional area about the neutral axis. So it's the same as it's been in our formula for bending stress, my over I. It's the same as the moment of inertia and BQ over IT. Same I. Right? So that's how you can get the shear force on each of those fasteners. Now, that's just the shear force. If you actually wanted the shear stress, that's actually easy to get. Once you get the shear force, shear stress on each fastener would just be that shear force divided by the whatever the cross-sectional area of the fastener is. All right, so most of these problems you'll see in this section just ask you for or deal with shear force, but occasionally I'm not going to, I don't remember off the top of my head. If one of them does ask you for the shear stress on the fastener, well, it's just the shear force divided by the area. Tau equals B over A. That's when we first introduced shear stress. So you take the shear force divided by the cross-sectional area of the fastener to get the shear stress. All right, any questions about this formula? Zach asked a question that was the next thing I was going to talk about. Was that this example we looked at here, we just have one row and nails going down the beam. But that's what we're going to talk about now. So what if we have multiple rows? All right. Any other questions? Because I'm out of space on this sheet, so I got to go to a new page. All right. So let's look at what if we have two rows of fasteners. For example, one of the very common places you see this used is if you have an existing I-beam. So this is a standard solid one-piece steel I-beam. Well, one thing that is commonly done to make it much stronger, increase the strength of this beam, is to attach a couple of flat plates to the top and the bottom of this existing I-beam. So that now, again, if I'll test my 3D scale, I'll see. Not too bad. But you take that existing I-beam and just take two flat steel plates and attach them to the top and the bottom. Now, again, here, if you're dealing with steel, one way to do it would be drill a bunch of holes and put some bolts in there. So you could come in and let's assume we're going to put in bolts, and we're going to put in 2 rows bolts. And same thing on the bottom down here, you would have bolts coming up through the bottom. Now, how this makes the beam stronger is what you're doing is you're increasing the moment of inertia. Right? What you're doing is taking this area here. That's the area that you're adding when you look at that cross section, and it's moved farther away from the neutral axis, so it's going to really increase the moment of inertia to that beam, which makes it stronger. It's a cheap, easy way to do that. But here, again, we've got 2 rows. Right, so now when we're looking at the shear force in these, in this case, bolts, we got 2 of them that's going to take that same shear force. So here, the shear force on each bolt would be VQS over 2I. Right? It's going to be half of what it was if we had just had 1 row of bolts. Right? Again, we just doubled the number of bolts, so the force on each one is going to be half. And also, again, when you're calculating this Q, this area here that we added, that would be the A prime that we use when we calculate that Q. It's the area that's attached by the fastener. What if we, say, took some boards and constructed a box beam? Let's say we did it this way. So say we took these 5 boards and nailed them together. So we took the 5 boards, arranged them like this, and nail these boards together. Again, we'd have nails coming up from the bottom as well. Yeah, picture's not too bad. But now we got 3 rows of nails. So shear force on each nail, VQS over 3I. So just like before. Now we got 3 fasteners to take that same shear force, so each one is going to take a third. And so, in fact, in general, this is probably, if you're looking for what formula you want. I can't spell general today. Just start over. In general, shear force on each fastener, it's going to be VQS over I times the number of rows. That's what I would suggest. If you're looking for, which formula you need to know for the test, that would be it. All right. So 1 row, 2 rows, 3 rows, it just, you divide the force by however many rows you got. All right. So now at this point, we're ready to see if we can work a problem. Any questions before we look at a problem? All right. Well, let's see if we can work one. Everybody good? I can move this. We'll start on a new sheet. All right. So let's try this example. We're told maximum shear force in the beam. So we're talking about the beam. This is V. Is 1,200 newtons. And we're told the allowable shear force on each, in this case, we're going to be looking at nails. So this is the shear force on the fastener, that's Fs. That's 156 newtons. So that's the maximum shear force that each nail can see. Now, again, that would come from whatever the material is being used and what kind of factor of safety, is required. That would determine what that allowable or maximum shear force on each nail is. And we want to find the maximum allowable spacing. For the nails. So we have a box beam. Let me draw this picture. I'll do my best. I should have started a little below that. I don't know. We'll see. I think I can make it work. So we've got this box beam constructed by nailing these 4 boards together. And these boards are nailed together in this manner. The nails driven down from the top. And we need dimensions, 20 millimeters, 80 millimeters, and 20 millimeters. And it's 100, and we would also have these nails, obviously the bottom is nailed on the same way the top is. And it's 120 millimeters wide. And each of these also 20 millimeters. All right, so that's what our box beam looks like. And we know the maximum shear force V that's acting on this is 1,200 newtons. And what we're trying to determine is what is this spacing? Right? What's the maximum allowable spacing? Right? If we spread these fasteners too far apart going down the length of this beam, then the shear force on each one is going to exceed 156. Right? We got to place them close enough together so that we have enough nails so that the force on each nail does not exceed 156 newtons. That is our problem that we're trying to solve. All right? So any question about what the problem's asking or the setup here? All right, so I'm going to draw, come down here and maybe I'll draw a new picture of a cross section. Let's see. Now, remember, we're using this formula, Fs equal to V, excuse me, VQS I times the number of rows. Right? Well, we know what Fs is. We know the shear force on each nail. We know what V is. That's given. The number of rows, we have 2. What we don't know or don't have that we need to calculate is what is Q and what is I. Right? S is what we're solving for. Now, from symmetry, right, this is a nice symmetric cross section. That's 120 millimeters wide. It's 120 millimeters tall. So I know from symmetry, the centroid is going to be right in the middle. So we don't have to calculate where the centroid is. Right? We get that just from symmetry. I know it's going to be right in the middle. So this is, I'll put, this is 40, this is 20, this is 40, this is 20. Right? It's right in the middle. So to get the moment of inertia about that neutral axis, again, we could do this a couple different ways, right? We've got, we could break this up into 4 rectangles and, add up the inertia for the 4 rectangles. But in this case, it might be less work, right? Think of this as like one big rectangle. In fact, it's square, 120 by 120, and then subtract the hole in there, which gets 80 by 80. 80 by 80. But one nice thing is, when we're looking at our neutral axis, the centroid for each of those is going to lie on the neutral axis. So we don't have to use the parallel axis theorem and do AD squared. We just take the moment of inertia for the big square, 1/12 base times height cubed, and I'm gonna go ahead and convert to meters. So 120 millimeters is 0.12 meters. Again, so this is just our 1/12 base times height cubed. Its centroid is on that neutral axis, so the distance is 0, so we don't have to add AD squared. And we subtract the moment of inertia for the little square. 1/12, the base is 80 or 0.08. The height is 80, 0.08 cubed. And its centroid also is on that neutral axis, so no AD squared. And combine those, I got 13.867 times 10 to the negative 6 meters to the 4. All right, any questions how we calculated I? Right, and if you haven't figured this out yet, come Monday on the test, you better know how to find the centroid of a cross section, and you better know how to calculate a moment of inertia, because that comes up in just about every problem in chapter 6 and 7.
I have a question. You got point zero eight from the inside rectangle. I mean, not rectangle, but square.
Yeah, you're looking at from here to here, that's 80. Here to here is 80. So I'm
Okay.
subtracting that moment of inertia for that area. That's where the 80 came from.
All right. All right. Thank you.
You're welcome. All right, now Q, remember, Q is based on the area that's attached by the fastener. So when you look at our cross section here, right, that's the area that's attached by those fasteners. All right, so this is my A prime. So when we do Q, and maybe we'll just call it Q nail. I don't know. So somehow or another identify. This is Q at the place on the cross section that nail is attaching this area. I don't know if you can think of something better, call it. Go right ahead, but just something to. This is not Q for all the area above the neutral axis. This is Q for the area attached by those nails. So it would be that area A prime times Y bar prime, where Y bar prime is this distance. Right? This is distance from the neutral axis to the centroid of that area A prime. Now, for our cross section, we go up 40 till we get to that, and then if it's 20, the centroid is going to be right in the middle, or half of 20. So that would be again 40 plus half of 20, which is 10. Looks like 50 millimeters. That's what Y bar prime is, the distance from the neutral axis to the centroid of that area A prime. So the area is 120 by 20, so 0.12 times 0.02. All right, yeah, 0.02. That's A prime, and its Y bar prime is 50.05. And we multiply all those numbers together. I got 120 times 10 to the negative 6 meters cubed. Right? Again, it's just the area attached by the fastener. All right, so now we've got everything except S. All right, so just take this formula, VQS over I times the number of rows. We're going to set Fs equal to the maximum allowable, 156 newtons. B was 1200. Q we calculated was 120 times 10 to the negative 6. S, that's what we're solving for. I was 13.867 times 10 to the negative 6. And we got 2 rows, right? So times 2. 2 rows. Let's solve for S. I got 0.03 meters or 30 millimeters. If you want to give it in millimeters, meters, it doesn't matter. As long as you got the right units, it didn't specify. So that's how close we've got to space these nails so that each nail doesn't have to take more than 156 newtons. Right? If you space them closer, then the shear force would be less than 156 on each nail. So that's even better. But this would be the maximum we could space them out. Anything over 30 millimeters apart, and the force on each nail is going to be larger than 156. All right, any questions about that one? While we got this picture up here, let's go back and do one other little thing. Let's go back to like the kind of problem we worked yesterday. What if we were asked to find maximum shear stress in the beam? Remember, tau Q over IT. Well, if we're trying to find the maximum, what we look at is the minimum thickness at the neutral axis. Well, for this problem, the answer is yes. So T min is at the neutral axis. So tau max is going to be at the neutral axis. So I'm going to draw a new picture. New cross section. Now, V doesn't change. We're using the same V at 1200 newtons. I doesn't change. It's the same cross section. Right? But what could change and what will change is Q and T in this case. Q here now, right, if we're looking at the neutral axis, we need Q at the neutral axis. So that means we need not just this area up here, right? We need all the area above the neutral axis, right? So we also have that area that we have to include. This is 40 millimeters. This is 20. Obviously, mine's not to scale. And there's 120 millimeters wide. And it's the same on this side. It's identical. All right, so when we do Q here, we got to do all this area. So we need, we call this A prime 1. We need that area times the distance to its centroid. And I didn't put this on here, but this is it's 20 millimeters wide as well. So we would have this area, which would be 40 by 20. So it would be 0.04 times 0.02 converted into meters, A prime 1. And we multiply times that distance to the centroid. Well, if it's 40 millimeters tall, it's a rectangle. That would be 20. So that's 0.02. Now, if we call this A prime 2, it's identical. It's what we did up here, right? So I'm not going to rewrite all this or recalculate it. We're just going to, that's where this comes from. 120 times 10 to the negative 6. Yeah, that's A prime 2 times Y bar prime 2. Right, we did it up here. Now, if this is A prime 3, it's identical to 1, isn't it? The question is, why are we only using the area at the top surface? Because, again, you go back to, well, we came up with this formula. Go back to the first page. Right, we're calculating this formula came from the shear stress at that point on the cross section. So we're getting the shear, that this formula corresponds to the shear stress at that point on the cross section. So when you calculate Q, you just use all the area above that. Now you could do the exact same thing if you calculate the stress here. You would use all the area below that, but you don't do both, right? So anyway, I got sidetracked. So we're just going to multiply this by 2. right? And now that takes care of area 1 and area 3. This would be area 2. So Q is going to be different. And so when we calculate this, I actually did this. I got 152 times 10 to the negative 6 meters cubed. Now, what would the thickness be at the neutral axis? Anybody want to volunteer? Correct. It would be 40 millimeters. The thickness neutral axis. Again, that would be, if you go across this neutral axis, any place that goes through that cross section, that counts, right? So the thickness at the neutral axis would be this distance, which is 20, plus this distance, which is 20. You add them together and it would be 40. That's where the 40 comes from. Again, that is the minimum thickness. You cannot go horizontally through that cross section and go through less than 40 millimeters. Right? Anywhere between this top board and the bottom board, you're going to go through 40 millimeters. Nothing less. All right, so I'm about to run out of space. I think I'm going to have to go to the top of the next page to see. Maybe I can keep everything. Yeah, y'all just going to have to. So let's go. So tau max, and that is the shear stress at the neutral axis. Again, it's dq over it. Again, this is at the neutral axis. So V was 1200. So V was 1200. Q, I just calculated 152 times 10 to the negative 6. I was same as before. It did not change. It was 13.867 times 10 to the negative 6. And then we just said the thickness at the neutral axis, 40 millimeters, 0.04 meters. And that would give me the maximum shear stress in the beam. Right? So this is in the beam. I got 0.329 megapascal. So not a real big stress, but if it's made out of wood, it's not going to withstand a lot of stress. All right. So that's really that part. What we just did is not new. That's basically what we did yesterday, but that was a good example. Last thing I'll leave you with, because we're right out of time here. We looked at this beam that we just did, right, and it was put together like this. Right, we had this beam nailed together like this. And so when we're calculating Q, this was my A prime, right? That's where we're calculating the shear stress using all the area above that. What if we had nailed these boards together a little bit differently? What if we had taken the same boards, but instead of nailing together like this from the top, what if we nailed them together from the side? Right, so we drove these nails in from the side like this. And so again, if you're looking down this, you'd see the nails that way. So everything else being the same, the only thing that would change would be Q, because the area that's attached, yeah, that looks like thing. Remember my picture. Something didn't look right about my picture. But what changes is the area that's attached by the fastener. Now this area, that's what you would use for A prime. So when you calculate Q, you would only use this area here, which is less than the area there. So Q is going to go down, and we could actually space these fasteners out a little more. But that would be the difference. Now, there's last thing, I'll share this. I think there's an example in a book like this where a combination is used. You got a box beam. It's put together like this, where, say, here it's fastened together by nailing down from the top, and then here it's nailed in from the side. Right, so on this side you got the nails driven in on the sides. Over here they're driven in through the top. So that might beg the question, okay, well now what do we do? Right, well, this is kind of a unique situation. If you got something like this, essentially you got to kind of break it up into two separate problems. Let's say we'll say this is B and this is C. So think of it as if you did it like it is at B on both sides, right, and solve that, which is basically just like the problem we solved today. That would give you the shear force on that row of nails. And then you would have to consider, well, what if they were both done together, like from the side? So now, if you had built this thing together like that, solve that problem, and that would tell you the shear force on the nails on that row at C. So you have to kind of break it up and look at two separate cases if you've got something like this. All right. Well, again, that's all the time. And again, this is where your test. Last thing you're responsible for on the test is this last section on the built-up beams. Any questions before I stop recording the session?
We're gonna have to memorize all these equations.
It's not that many. We'll talk about it tomorrow. Trust me. You got the bending stress, MY over I. You got shear stress, VQ over IT. You got the built-up beams, the VQS over I times the number of rows. Q is A prime times Y bar prime. Moment of inertia for a rectangle, 1/12 base times height cubed. That's about it. You got about 5 or 6 formulas. That's it.
All right.
Right. Anything else before I stop? All right. I'll stop recording.